Okay, so let's start with the basics for this course, which will be understanding properly what rings and fields are, or just recapping this, since this is going to be one of the main things that we study. So I want to make sure everyone is on the same page. So chapter 1 is called number fields. This will be the main object of study of the course, and our first section, 1.1, is just a recap on rings and fields. So, recap on rings and fields. So, let me start with a definition which you've hopefully seen, but let me just remind you what a ring is. So, this is definition 1.1.1. So, what's a ring? A ring, R, is a set together with two binary operations on it. Together with two binary operations. These are usually denoted as like plus, and you have times. You have these two operations, and you have some sort of properties you want this to satisfy. So you want these operations to be such that, firstly, R with your addition is an abelian group. So, i.e., we have, for example, the element 0 is contained in R, and if R is in R, then you have an additive inverse. Then minus R is in R. Okay, so we want it to be an abelian group under addition, and for multiplication, we want it to be associative and distributive. Multiplication should be associative and distributive. So what does this mean? So if you have xy times z, it doesn't really matter how you put the brackets. So this is your associativity. I'll put this in brackets. Associativity and distributivity is you have x, y plus z. This is xy plus xz, and similarly y plus z times x. You want this to be y x plus zx. Note that I'm not yet assuming that the ring is commutative, but that is the thing that we're going to assume throughout the whole course. So a ring is called commutative if for all x and y in R we have x times y is the same as y times x. All of our rings are going to assume to have this. For me, commutative rings always contain a 1, so I'm going to assume that they have x and y equals y times x, and have an identity element. Identity element denoted 1, i.e. x times 1 is always 1 times x, which is just x. This is what you want your identity to have. Sometimes having a 1 is called being unital, but for us, all of our rings are going to be commutative and going to contain a 1. And the last thing I want to write is, lastly, the subset of elements of R which have a multiplicative inverse is denoted by R with a little cross like this. So these are all the elements x and R such that there exists a y in R such that xy equals 1, which also equals yx, because I'm assuming my rings are commutative. So these are a set of units. These are called units. Units on our ring. Okay, so as I said, throughout our course, our rings are always going to have 1, always going to be commutative, always going to stick to these conditions, because this is the setting in which the rings that we'll study will fall under. From number fields, we're going to construct these rings of integers, and we're going to study their ideals, and so on. And all of these rings are always going to be commutative. Here's another definition which you might remember, that is of an integral domain. So we want our rings to be nice. So it's definition 1.1.3. The numbers will skip because I'm trying to keep track with the notes that we have, the typed notes, and there's like extra remarks or stuff written in, so they take up their own numbers. But I want to keep parity with the numbering system, so that's why I'm skipping numbers from 1.1.1 now to 1.1.3. The 1.1.2 is hidden in the notes. You can go have a look at there. So definition 1.1.3, we say a ring R is an integral domain if for all x and y in R we have xy equals 0 implies x equals 0 or y equals 0. So if you have a product of two elements which is 0, one of them has to have been 0, or both of them. Great. Again, most of all our rings will be integral domains as well, I think. Let's continue with our definitions, given that we're just doing a recap. So definition 1.1.4, this is the definition of a ring homomorphism. So these will be quite useful for us. So we're going to play, it's quite convenient to have ring homomorphisms or be comfortable constructing them, because a lot of the time you want to prove something about one ring, it's easier to prove it about another ring, and then you just like map between them if you can. So this is what the idea. So let R and S be rings. Then a ring homomorphism phi from R to S, R to S is a map such that well, you want it to preserve the fact that you're a ring, so you want to preserve addition and multiplication. So you want phi of x plus y to be phi of x plus phi of y. You want phi of xy to be phi of x times phi of y. And you want to preserve these our identity elements. So phi of 1 you want it to be 1, and phi of 0 you want it to be 0. Great. And just for notation, a ring homomorphism is called an isomorphism if it's bijective. Equivalently, if it's injective and surjective. So here's an example. The map. So you take the integers and you reduce them mod m. So let me go 5 from z to z mod n z, defined by x maps to, this is this arrow, it denotes maps to, so this is telling me what the element maps to, x to, you do x modulo n. This is a ring homomorphism. You can check this. It's a nice example if you exercise to refreshen your minds on this. So this is a ring home. So let's continue with our raft of definitions that we all already know. So I let phi from R to S be a ring homomorphism. A ring hom, I'm going to start shortening it too. The kernel of theta denoted, curve phi. This is the set of all elements x in R such that phi of x equals 0. This is what's called the kernel. Remember this from your algebra 1, your linear algebra thing. The image noted im theta. This is the set of all how do I say it? Let's do this. All S in S such that there exists an R in R with phi of R equals to S. So it's all the little things in all the elements in S which get hit by some element in R. This is our image. And if you've done algebra, you'll remember that these things that you have like a similar for groups. You have like isomorphism theorem for rings, and so on. So here are we've already talked about some of this, but some examples of nice rings that we're gonna see. Here are some examples of rings. In case I've already given you a few, but in case you don't remember, so like 1, Z, the integers, this is a ring. And in fact it's commutative and an integral domain. This is a ring, which is also an integral domain. Maybe later I'll start becoming lazy and instead of integral domain I'll just write ID. 2, for example, polynomials in one variable, so z of x. This is also a commutative ring. And in general, if R is a ring, then Rx, the set of polynomials with coefficients in R, is also a ring. Okay, so this is our very quick recap of what a ring is. And now let me move on to something that shows up in the title of this chapter, which was number field, so the word field. So if you know what a ring is, now you should try to remember what a field is. So here's definition 1.1.8. So a field F is a commutative ring. Well, I'm not saying why I'm writing commutative because we assumed it always, but it's a commutative ring such that every non-zero element has an inverse, multiplicative inverse. Equivalently, we just want f of the set of units to just be your field F, take away the element 0. So every element has some inverse. So some examples, one, like the rational numbers. This is a field. The real numbers, the complex numbers, these are all fields. Fields, maybe a field of finite size, so z mod pz for p a prime. This is a field. So this is the integers modulo p. Here's a non-example. So non-example. So this isn't a field. examples are like the integers, zx, for example. These things aren't fields, or like z mod 4z. This is also not a field, not a field, or not fields. None of these are fields. So if you want to take z mod something, you want to make sure that the something that you've modded out by is always a prime number. If you've modded out by something that's not a prime number, then you won't get a field. Because you'll have a if you here in this case in z mod 4z, you have this isn't an integral domain, and so because it's not an integral domain, it means that you can find two elements which multiply to 0, which aren't 0 themselves. But then if you think about it, these elements can't possibly have an inverse. So this is why these things can't be a field unless your thing was prime. Great. So this is a recollection of what a field is. So now let's start to some of the stuff that we're going to really play around with a lot. We have to try and keep more stuff on the page. So here's definition 1.1.11, which is that of an ideal. So let R be a ring. Then an ideal, I'll try and use like square A. This is Gothic A, for me it's like a square A. This is a subset of R, which is an additive subgroup of R. So it's closed under addition, it has the element 0, and such that for any R and R, we have, if you have any R and R and A inside of my ideal, we have A times R is also an element of my ideal. So if I take an element of my ideal, multiply by any other element of R, and I always land inside of my ideal. This is what an ideal is. So here's probably the most important example of an ideal that we will look at. So example, so let R be a ring, and take an element R and R. Then we let, so I'm just going to turn it by brackets R. This is the ideal generated by R. So this is a set of all R times X, such that X is, changing my lines. Yeah. Okay. Sometimes I'll use this straight line for such that, and sometimes I'll use 2 dots apparently in the notes. It should mean the same thing. So it's a set of all multiples of R. So I'll call this is called the ideal generated by R, by little r. Great. Technically, so this is generated by, I've taken an element of R, I've generated an ideal from it. Because I've only used one element to generate it, this is called the principal ideal. In fact, I'll say this is known as a principal ideal. But you can do a similar construction if you take more than one element. So you won't get a principal ideal, but you can get other types of ideals. So more generally, if you have like R1 to Rn elements in R, we set this R1 comma Rn. This is going to be the ideal. Well, as a set, this is what it looks like, and you have to check that it's actually an ideal. So this is, you take finite sums, sums from I equals 1 to n of Ri times Xi, where Xi is just some element in R. So as a set, this is the ideal generated. So as a set, this ideal just looks like linear combinations of my elements in my chosen elements. This is called the ideal generated by R1 to Rn. You can check that this set actually is closed under addition and contains the element 0. So this is an ideal. But this isn't a principal ideal. This is just an ideal. So these two sort of ideals are important. We're gonna, towards the later bits of the course, what we're going to be studying is we're going to be studying special rings. We're going to be studying the ideals in them, and it turns out that principal ideals like this one are very easy to deal with. But once you start getting ideals with more generators, things get more and more complicated. And we're going to have rings where we're going to want to study if an ideal is generated by a single element, so if it's principal, or if it isn't. And we're going to somehow define a measure on this. We're going to measure how far an ideal is from being principal or not. Well, maybe not an ideal, but how far a ring is to having all of its ideals being principal or not. This is going to be something that's important, so you sort of do want to get your head around these sorts of ideals, because we're going to be seeing them a lot. Let me just note that the ideal generated by 0 is just sometimes denoted by 0, and the ideal generated by 1 is the whole ring R. Because, yeah, just run through the definitions. So here's, as I was just mentioning, so talk about the principal ideals being important. So here's a definition, 1.1.13. If, let's let R be a ring, if for every ideal frac A in R, so this is my notation for an ideal in R, I probably won't distinguish between this symbol and this symbol, so don't take it at my if I want to assume that my ideals aren't the whole ring or aren't trivial, I'll specifically say it, but these two symbols will basically both mean just included. It could be the whole thing, or it could be none of the whole thing. I'll specifically say if the ideal is not allowed to be the whole ring, for those of you who know. Anyways, if I have a ring, if for every ideal A and R, we can find some little element A and R such that the ideal generated by, the ideal frac A is the same as the ideal generated by little a, then we call R a principal ideal domain. Domain. Oh, and I realized that I said let R be a ring, but I want to let R be an integral domain. Let R be an integral domain. Then we call this a principal ideal domain, or this is usually just denoted by PID for short. Great. So we're hopefully at speed. We're recapping a lot of some of the definitions that you should have seen in the previous algebra courses. So hopefully you've seen all of these things before. We're going to be studying, basically for our specific number theoretic rings, we're going to be studying if they're PID or not. That's like a very important question. But anyway, we still got to continue with this recap. So here's another definition. 1.1.14. And let R be an integral domain, so an ID. We say an element little r in R is irreducible if whenever R equals A times B, if you can write it as a product of two things, we must have exactly one of A and B being a unit. So you can multiply as if you can write it as a product of two things, one of those two things always has to be a unit. That's what if that's the case, then we call that element R irreducible. The reason I'm introducing this is because we're going to be studying irreducible elements in like rings of polynomial rings, which will be irreducible polynomials, and these are going to define us our number fields and so on. So here's hopefully another definition which you'll remember. As I said, this first lecture is just a recap of things you should know. So it's just a lot of definitions which I want you to know and make sure you've seen before. So an integral domain in which every element can be written uniquely as a product of irreducible elements. Irreducible element is called a unique factorization domain. You might have seen this before, so I've just done UFD for short. Maybe I should say here uniquely up to units. Up to units. So somehow, just like you can write the number 6 as 2 times 3 or minus 2 times minus 3, there's the units don't really change our ability to be a unique factorization or not. And then lastly, for a moment, the last definition I want to end this first section on is that of a quotient ring. This is usually where people struggle the most, although you might think it's very simple, but we're going to be dealing with quotient rings a lot, or in parts of proofs, and usually it takes a while for people, for all of us to get our head around what quotient ring is. So I want to introduce it, and then we'll be seeing a lot of examples of these things later on. So I'm going to let R be a ring, and A an ideal in R. Then the quotient ring R mod A is the ring whose elements are of the form. So you have the element R plus A, so I think of these as like cosets. R plus A for R and R. Where, so this is what, as a set, this is what the elements look like, and what's my addition and multiplication. With addition and multiplication given by, so as follows: R1 plus A, R2 plus A. So these are two elements. What is this to be? This is going to be R1 plus R2 plus A. That's my first. This is how I do addition. And R1 plus A times R2 plus A. This is just R1, R2 plus A. And I'll leave you as an exercise to check that this is well defined and that this has I'll let you think about what the unit, the 1 is, and what your 0 is in this ring. Okay, so I'll stop here for this first part.